All right, guys, let's talk about the movement of electrons, which is going to be lesson 4. So we've talked about the Bohr model, and then the last lesson you drew it. So today we're going to talk about what happens in the Bohr model. So Niels Bohr adopted Planck's assumption, and because of that, we were able to explain the following. Electrons in an atom can occupy a certain energy level. Electrons are permitted to have energy levels that have specific energies, and these energies will not be radiated from the atom. And the energy absorbed or emitted in such a way as to move an electron from an allowed state energy level to another energy level. And that's where we use this E equals h nu, where h is Planck's constant and nu is frequency. So there are two kinds of states that the electron can have. A ground state is when the electrons will occupy the lowest available energy levels. That's what you're going to see when you look at your configuration on the periodic table. And then there's an excited state. This is when the electrons no longer occupy the lowest available energy levels, and that will have a different electron configuration. And that will have electrons in different energy levels other than what they are when the electrons are stable and grounded. So let's look at some possible excited states for sodium. On your periodic table, if sodium's electrons were in all of the rings in the Bohr diagram that they were supposed to, it could have a ground state configuration of 2-8-1. An excited state for sodium would be 2-7-2. Another possible excited state would be 2-6-3 or 2-5-4. They all have 11 electrons in them. If you were to add 2 plus 8 plus 1 is 11, 2 plus 7 plus 2 is 11, 2 plus 6 plus 3 is 11, and 2 plus 5 plus 4 is 11. What's happening here is that in this excited state, you have one of the electrons from the second energy level is being kicked out to the third. And in this one, you have not one but two electrons are being kicked out to the third energy level. And in this one, not two but three electrons got kicked to the third energy level. So how do you tell if the electron configuration is ground or excited? You have to add up the total number of electrons in the configuration first. Then you have to determine the element. Then, if it matches the element's configuration on your periodic table in your reference packet on page 9, that's what we will consider to be the ground electron configuration. If it doesn't match, it's what we call the excited one. So, for example, if we were to identify the electron configuration as being ground state or excited state for fluorine, we would look at this. So 2-6-1, is that the ground state or is that an excited state? So when we look at this, we have 2 plus 6 plus 1, that's 9 electrons, so we're talking about fluorine. And when we look at your periodic table, the configuration on your periodic table says 2-7. So this configuration, 2-6-1, is the excited configuration for fluorine. When we look at more examples, if these were the given electron configurations, the electrons add up to 21, so that's scandium, Sc. The electron configuration on your periodic table says 2-8-8-3. Does this match what's on the periodic table? Yes, so it's the ground state. Here for sodium and silica, we have two excited states because our given configuration in the problem does not match what's on the periodic table. So those are both going to be excited states. Remember, when it's in an excited state, the total number of electrons does not change. The thing that does change is their placement. Where are we placing them in those rings around the nucleus of the atom? So, your practice problem. Identify the electron configuration as being ground state or excited state. So 2-7-3. 2 plus 7 plus 3 is 12. An element on the periodic table with 12 electrons is magnesium. The electron configuration on your table is 2-8-2, so this configuration is for a magnesium atom that has electrons that are excited. Check your understanding. Give a possible electron configuration for calcium in the excited state. Now, there's going to be multiple answers to this, and we're going to go over this in class tomorrow. When we talk about electrons in their excited states, we're going to talk about what happens. What happens and what we see is, as people, is we see spectra, bright line spectra. So we have emission spectra. So another mystery involved the emission spectra observed from energy emitted by atoms and molecules. So what happens is when these electrons jump to energy levels that are outside of their ground state and they're excited, eventually all of that energy that they gained is going to be released again. And when it releases that energy, it releases it in the form of light. So what we have is we'll have a bright line spectrum, and one does not observe a continuous spectrum as one gets from a white light source. So if we were, and we're going to do this in a lab actually, we're going to look at white light and we're going to look at different elements and the spectra that they give off. Different elements will give up different spectra. Right down here on the right hand side is the spectra for the top one, sodium. Sodium, when sodium burns and its electrons jump from an excited state back down to a ground state and relax, they release yellow light. Hydrogen will release two purple lines, a blue line, and a red line. And we're going to see a sample of hydrogen, and we're going to see sodium when we do that lab. Only a line spectrum of a discrete wavelength is observed. So sodium will give off yellow light at about 590, and hydrogen gives off spectra purple line at about 410, 435, 485, about 650. So those lines are specific to hydrogen. And anytime you look at a sample of hydrogen and you look at its spectra, that's what you'll see. Now, absorption is when electrons absorb energy as they move to higher energy levels, when they move to the excited state. This excited state is temporary and unstable. So it's like what we talked about in class. You eat a bunch of candy and you get this sugar rush, this large amount of energy. It's only temporary. It doesn't stay that way for very long. Emissions are electrons. We know electrons are negatively charged and therefore attract to a positive nucleus. So eventually, these excited electrons will fall back to the ground state and give off the energy they absorbed as light energy. And that's why we see colors. So if an electron is moving from a lower energy level to a higher energy level, it will absorb energy. It'll get the energy in order to make that jump. And then when it emits energy and falls back from an excited state, so when it falls down, it will emit that energy in the form of light. So the color of light is determined by how much energy is lost by the electron when it drops back down to the ground state. So if it does a big jump, it'll be in the purple range. If it does a really small jump, it'll be in the red range, and then the other colors in the spectrum fall within that gap. So we have examples. Possible ways an electron can fall back to the ground from this fourth energy level. So it'll go from the first to the fourth energy level. It could go from the fourth to the third, then to the first, or it can go from the fourth to the second to the first, or from the fourth to the third to the second to the first. And so we can get a different range of wavelengths in light, and that's how we get to see different colors. So our bright line spectra is kind of like a fingerprint. So each element on the periodic table has its own bright line spectrum that is unique. So nobody else on that periodic table has a spectra that looks like hydrogen's does. Hydrogen's is specific, and we can use that to identify unknown mixtures of gases. This is how we figure out what stars are made of. When we look at how stars burn and the colors that they emit, that will tell us what element is in those stars, and that's how we can figure out what they're known from. So for example, what gas comprises the unknown A? So unknown A has these specific wavelengths, and as you can see, gas A has a single line, a double line, and a single thicker line, and so does our unknown mixture. So we can say for sure that we know that gas A is in our unknown mixture. Gas D has this single line at this wavelength and these double lines at this wavelength. So again, gas D is also in our unknown mixture. it's kind of like you're just matching it up. So when we're looking at mixtures of different gases, okay, so for our check your understanding, we're going to talk about the answer to this in class. Each line on the visible light spectrum represents what? Electrons jumping to the same excited or energy level, electrons falling back down to their ground state from the same energy level, or electrons jumping to multiple excited states or energy levels, electrons falling back down to their ground states from multiple energy levels. We'll answer that one in class, but I want you to think about it. What does that actually mean? And then for this one, check your understanding, I want you to figure this out. What gases are in this unknown gas when we look at gases A, gas B, gas C, and gas D? Remember, each gas has its own individual fingerprint, and our unknown gas is a mixture of them. So when you answer this question, you want to match up which gases are comprised in our unknown mixture. We're going to talk about that tomorrow in class.